Thank you, Dirk. It's a pleasure to be here and honored to be talking to this really extremely distinguished group. I've been looking at the list of speakers, and I think this may be the best conference list I've ever seen. It's completely amazing. The slide you're looking at was the cover slide of my Nobel talk. It was called Auction Theory Evolving Theorems and Applications, with asterisks by theorems because there's some other stuff, some simulations and experiments in there too. But, and I wanted to talk about the evolution of my thinking, and that's what I did in the 2020 Nobel lecture. And then I was asked if I could give an extended version of that today. And what I decided to do instead, actually, I am going to start with the reprise of my official Nobel lecture, talk about the evolution of the work. But, you know, I saw this group and I didn't just want to give an old man talk. I'm still a researcher. So I decided I would do the second half reporting some new research. And this is something nobody has seen yet, except my co-author, Mitch Watt. This is research that's being reported publicly for the first time today. So it's a little bit risky to put it next to the Nobel lecture, but what the heck, you know, that's the spirit of who we are, is it's not just celebrating old work. So with that, I also wanted to say, you know, when the Nobel Prize was awarded, it was very strange in some ways. I look back at all the people I've written with, and these are just the papers. This isn't even all my papers. I have more co-authors than this, but these are co-authors and collaborators that I worked with on projects in market design, and so many of them contributed so much, and it's really hard to figure out, you know, how you pick out one person to give a prize to. So I'm going to talk a little bit about this past work, and you'll see all of these pictures again. But the it really it's a community of people who earns the prize, and I just wanted to make that clear. Okay, so the earliest work that people know, I think, of mine is largely done with Bob Weber, where the goal was to extend the VICKREY and Wilson models. So VICKREY had introduced what we now call the private values model. Wilson had introduced what we call the common value model. We wondered how those fit together, and we put a model that did incorporated both. And we asked what were questions in the day that were, you know, questions that were bouncing around. How do expected revenues compare? We had the revenue equivalence results dating from VICKREY and going through Meyerson. And what about information policy? How does the seller benefit by revealing information? That had come up in some practical applications. And in that paper, we showed that in our model, and you know, we reported it a little differently at the time, but here I focus on, all we really did was prove that a certain strategies form symmetric Nash equilibria, symmetric increasing Nash equilibria. And in those, we showed that the expected price was highest in our model from the English ascending auction, and next from the VICKREY second price auction, and lowest from sealed tender, and that the expected price is higher in all of them when the seller shares certain relevant information. These are all very model-specific conclusions, but anyway, it's the Nobel Committee liked it, and so did some of you, so it's sort of the first thing on the list. My own thinking, though, you know, Bob had encouraged me, Bob Wilson, who was my advisor, had encouraged me to think about auctions, because we were thinking about, you know, where did prices come from? There were these paradoxes, confusions about whether prices come. I'm looking at Pradeep down there, who also was driven to work in this same sort of direction. But Bob wanted to know, after the Grossman-Stiglitz paradox came out, where the people were trading using information. They were price takers, so they couldn't affect prices, but somehow their information was already reflected in prices. It was a conceptual puzzle for many of us. So my own thinking developed through a couple of steps, and one of them was the auctions only had offers on one side. What if there was trading? What if there were buyers and sellers? And what if we started with the simplest case? And this is Nancy Stokey here, who I worked with on this problem. And the idea is that how can buyers and sellers both protect themselves from the winner's curse, with the winner's curse being what Bob had studied, what I'd studied a little less in connection with auctions. And we proved the no trade theorem, which was that if risk-averse buyers and sellers with different information, but the same prior beliefs are mutually aware and they both agree to a proposed trade, then that trade has to be the zero trade. And it was just, it's a common knowledge result, really. Common knowledge that trade occurs, rationality. And it begins to get at how it can't be differences in opinions about the value, differences in information about value alone that's driving trade. You need both some reason to trade in addition to private values. And we were still struggling with how the information how my information could get into prices when I'm a price taker. And sort of the next step along the way was a paper I did with Larry Gloston, which attempts to resolve the Grossman-Stiglitz paradox using a model of intermediated two-sided trade with both some traders having private value, some having common value, any mix really of private and common values. And what we did is we were asking the question, suppose that the market works the way financial markets work then, so-called specialist markets. You have these intermediaries or specialists who are naming prices. How does information, and remember, this is very different from general equilibrium theory, which didn't tell us where prices come from. They just appeared to clear markets. Here we have, self-interested intermediaries who are competitive and earning zero profits. What would they do? And if I'm a bid and ask price taker, can my information be reflected in the price at which I transact? And the answer turns out to be yes, even though you're a price taker. And the reason it works that way is that the bid price ends up being the expected value, from my perspective, if I'm the specialist or intermediary, the price I offer to you is the expected value conditional on you deciding to sell to me. That's the equilibrium price. And the equilibrium ask price at time t is the expected value conditional on you buying from me. And it's always the case in these models that if there's private information, that the ask price strictly exceeds the bid price. The specialist, and by the way, for there to be any trade at all, there has to be some private motive for trading. The ask price always exceeds the bid price. The price that trade actually takes place at is the ask price if you buy from me, and it's the bid price if you sell to me. And consequently, some of your information, it's reflected in your action of buying or selling, is going to be reflected in the price. If you have favorable information, you think the security is undervalued, you buy, and its price goes up, even though you're a price taker in this extended sense of not affecting the bid and ask price. And we showed that we studied this market and showed that the transaction prices of associated public information form a martingale because the information that you're conditioning on is true information, and it's information that evolves over time and comes out in the market, where PT is the price process, and that's the sigma field that's generated by the price process up to time t. Okay. So that was what we were doing in connection with financial markets. I also did some work with Marissa Beck and Nick Arnosti on display advertising. And in the early days of display advertising, as we moved into there actually being bids, there were display advertisers on the internet who would just say, I have a sale at my Ford dealership this weekend, show the ad to everybody. And performance advertisers who would target you based on your characteristics. And we created a model in which the value to an individual bidder was a common value. So maybe Dirk is a high income guy who's very responsive to internet advertising, and everybody cares about that. There's also a match value. He needs a car this weekend, or he's shopping for sporting goods this weekend, so that different advertisers have different specific values for him. And we wondered if we could create an auction that would work well in that setting. And the main theorem from that paper, if you have a set of auction designs that has these 5 properties, it's got a deterministic winner selection rule. It's strategy proof, it's truthful. It selects an efficient assignment among the performance advertisers. Basically, that means the highest performance bid is going to win if any performance bid wins. It's free of adverse selection for display advertisers. So that means that the distribution of common values that the display advertisers gets when it wins is the same as the a priori distribution of common values. And it's false name bidder proof. Nobody can manipulate the outcome by putting in another losing bid, especially a low losing bid. Then we showed that this set A is a 1-parameter family in which the performance advertiser wins when the ratio of the 2 highest bids exceeds some parameter alpha. This is the 1 parameter in the family, which is greater than or equal to 1. So this gives us a full set of strategy proof, and this is we call it a modified second bid auction, and it's a way of solving a particular problem of eliminating adverse selection for the display advertisers. And I guess one of the things that the committee was particularly happy about was the simultaneous multiple round auction. When in 1993, when the U.S. government decided to sell radio spectrum, there were a whole bunch of interrelated licenses for sale. It didn't have a lot to do with the one object theory, but they had a lot of citations that they'd written into the notice of proposed rulemaking mentioning work of Wilson's and mine and other people's. The guy in the lower right here is Evan Correll, who is the fellow who wrote the notice of proposed rulemaking and was a driving force behind a lot of what happened in the auctions in the government. Preston McAfee had a proposal, Preston there in the upper right, that was very similar to what Bob and I did. We had a few extra innovations in ours, but that the FCC ended up adopting. So basically the rules that Bob and I proposed were the ones that were adopted. But we were concerned at the time, how can bidders avoid buying multiple items that are substitutes if they're bidding simultaneously? And how can they know what the prices will be to buy the best ones? And there were 2 sorts of proposals made. Things where items were sold in sequence, so you could avoid buying multiple items because once you got what you needed, you stopped. Or if you did things simultaneously, what you could do. And I was motivated in this by, personally, so this is a story I told in my Nobel lecture. I had recently been to a charity auction. I don't know how many of you still see these silent charity auctions, but there'll typically be a table and there are multiple items that are available for sale all at the same time. And some of them will be pictures and it'll say it's a vacation in the Caribbean or it's a night out at a restaurant. And there'll be a sheet where everybody signs up and you can write your bid and you can outbid the guy who bid before you. And in this way, you could, look at what the relative prices were in bid. But there was a critical flaw with them, namely bid sniping, which is to say that if the silent auction in a charity event might be before dinner, maybe it ends at 6 o'clock. And so what you do is you find an item you're interested in and you wait till 5:59 and you go pick up the pencil and you slowly write down your bid just before 6 o'clock and don't give anybody an opportunity to raise your bid. And a lot of people were actually doing that. That was part of the game that they were playing in these charity auctions. And so what Bob and I did when we created the simultaneous multiple round auction is we added this thing called an activity rule, which forced bidders to be active early in the auction if they wanted to still be active late in the auction. We did it in a series of rounds, and we arranged that the auction would never close until there was a round with no new bids. So we didn't allow bid sniping, basically. We ruled it out by the rule change. And that turned out to be pretty successful, and we ended up having some good auctions. And I proved that if goods are substitutes and bidding is straightforward, then the prices and allocations converge to an approximate competitive equilibrium. There's lots of similar work by others, actually, so this is not especially unique, but it was the idea that motivated what we were doing in the in this. Really, at the time, I didn't know that Kelso-Crawford work. Kelso and Crawford really deserve a lot of the theoretical credit. The activity rule, however, was what made it practical to use for this design. Okay, I have a paper with, I started talking with Al Roth, and we taught a class together on market design in 2000 based on what he was doing in matching and what we were doing with auctions. And one of the questions we had is the matching mechanism introduced by Gale and Shapley, which had no rule for prices. Is it mathematically connected to Vickrey's price-based auction mechanism? And Hatfield and I wrote down a model of what we called the matching with contracts. In both mechanisms, it's a dominant strategy for the bidders to make truthful offers if there's a single item, you're buying a single item, or if you have a single match. And in both mechanisms, if the offers are substitutes, the outcome is the core allocation that's most preferred by the offerers. And what we showed is that these two mechanisms are both special cases of a matching with contracts mechanism, which also includes some other mechanisms that share these same properties. So we connected in this way, actually connected the Vickrey auction with the Gale-Shapley mechanism. The question of bidders who were, when the items are not substitutes. So the problem is that bidders wish to buy a collection of licenses that's sufficient for a business plan without the risk that they might along the way get stuck winning a non-viable subset. So with Peter and Larry and Bob Day, we created a combinatorial clock auction. We wanted to know how bidders could identify and bid on relevant packages, and what pricing rule creates the best incentives for ensuring competitive revenue. And there were a couple of papers in this. I'll just comment on one that Bob and I showed that an auction minimizes the sum of the bidder gains to bidding untruthfully and provides competitive revenue from truthful bidding if and only if it's what we called the minimum revenue course selecting auction, which was a class of auctions that we described in that paper. We were able to characterize some properties that this was novel in that we made the incentive compatibility, we put that into the objective function and we put the revenue into the constraints, which is sort of a flip from what everybody else was doing, but to say, well, we've got to get this much revenue. What's the best incentives that we can provide? And we optimized in this flipped sort of way. In work with Kegel and Yen-Chen Lin, we wondered the number of packages that people have to bid on in a Vickrey auction. It explodes with the number of items. If you have n items, there are 2 to the n packages. Nobody bids on all of those. Is it enough to bid on relevant packages? What are the relevant packages? And so we showed that if bidders bid to their limit on certain packages, which were we characterized what were the efficiency relevant packages and the core relevant packages, then the final allocation will respectively be efficient or in the core. And these are the core relevant packages mean you have to be bidding the relevant package that you would have bid for a constraining coalition that forces the winners to pay a certain amount and land in the core. So this was, again, trying to get at something practical where bidders weren't bidding on everything. What did they need to know? And if bidders were just bidding for the packages that seemed most valuable in an ascending price auction, we found that in experiments paired with simulations, that auto bidders that look at the current prices and bid on the tentatively most profitable packages simulate and do a pretty good job of predicting the outcome of student bidders in a laboratory. So we found we could tell when we were going to get the kinds of results that we wanted. Okay, the last of the big challenges that in the first part of this talk is about the incentive auction, which is the most complicated project that I ever worked on in my career. Again, Evan Correll pops up as the guy who drove this forward. He worked with John Williams, shown here, in proposing this to the government and getting them to adopt the general approach. But the idea was that the idea emerged in, basically in the president's broadband plan in 2010. In the Obama administration, we had recently had the iPhone had been introduced, and there was huge demand for spectrum for mobile uses, and there wasn't spectrum available that was suitable for the mobile uses that were at the time. And the idea was to buy some of the television broadcasters' broadcast rights and repack the remaining broadcasters into a smaller set of channels so that we could create some licenses that would be used for mobile broadband. We had to decide how many and which broadcasters to get. And this is this graph here, which some of you may have seen, is shows the interference patterns in the United States. This is a simplified representation, but the idea is if each node in this graph represents the location of a television station, and each edge in the graph connects two stations, if they can't be assigned to the same channel without creating radio interference. And the point here is, this is quite a dense and complicated graph. And let's see if I say the idea was to free the TV channels that are redeveloped for mobile broadband use and sell the mobile broadband licenses to television companies. Now, in the course of doing that, we have to figure out what the feasible allocations are. Which sets of channels can we buy if we want to clear, let's say, channels 38 to 51? Which broadcast TV stations do we have to buy to do that? We have to ask ourselves if the stations that remain on the air are going to be in the smaller set of channels or non-interfering. How do we assign channels to stations? And that's a classic problem in computer science. It's a graph coloring problem. It's the same as asking, given a graph and a fixed number of colors, is there any way to assign a color to each node so that no two connected nodes are the same color? Here we're assigning channels to each station so that no two connected stations are on the same channel. And these are the so-called co-channel interference constraints. That wasn't all the constraints in the problem, but it's a reasonable representation of the main constraints in the problem. And that's an NP complete problem that is just checking whether it's possible, given a set of stations, to assign channels. And we had to somehow optimize on top of that. It was a mess. So the challenge was to buy rights and reassign the stations optimally. That's a large-scale NP-hard problem for which optimization is impossible. And I worked on this project primarily with Ilya Segal and Kevin Leighton Brown. Kevin taught me practically all the computer science I know along the way. That is how to approach this problem and how to get the answer most of the time, even if we couldn't get the answer all of the time. And with Ilya, we worked on, given what was computable, we worked on designing an auction that we could implement given the computations that were possible. So it was really quite a challenge. And the new class of descending clock auctions that we created had several really interesting properties. First of all, it was strategy proof. We learned from Sheng Wu to call its property obviously strategy proof. At the time, what we wanted was, we said, we wanted an auction. We said, well, we can't promise how the computations will work out. How do we think about strategy proofness? And we wanted an auction that would be strategy proof even if we made computational mistakes. And Sheng Wu twisted that into What does it mean to be strategy proof, even if you're not quite sure what others are going to do or what the rules are? Some notion of simplicity, which is related but a little different than what we were conceiving. We wanted an auction also that was budget compliant. If we had a limited amount that we could spend, we wanted the auction to satisfy the budget constraint. If we have $15 billion to spend, we can't run an auction that costs more than $15 billion, and we can't run a VICKREY auction that we just cancel if it's too high, because then it's no longer strategy proof. That's not a VICKREY auction anymore. So it needed to be strategy proof and budget compliant, and needed to accommodate limits on computational power. And as Ilya worked out, it was uniquely privacy preserving. It had this characteristic that all you ever learn about the seller's value is that it's low enough that they're willing to sell at the price. And you never learn anything more than that. And this is the new class of descending auctions that we invented and implemented in this $30 billion worth of transactions, buying and selling transactions. Okay, additional recent papers with Mohammed and Chen Wu and Scott. We have a paper on investments in these approximation mechanisms with Martin and Gregor in the second column. We have a paper on taming these are working papers, all of them, on taming the communication and computational complexity of combinatorial auctions, with Josh Mulder down here. Well, one of our papers is now forthcoming. Two of our papers, actually, in Econometrica and the Journal of Economic Theory on refining predictions of Nash equilibrium in a useful way for auctions, with Neil Newman along with Ilya and Kevin, some simulation experiments. But what I'm going to turn to next is brand new work that hasn't been presented before, and it's with Mitch shown over here, Mitchell Watt, on linear pricing mechanisms in markets with non-convexities. I really wanted this not just to be an old man talk about all the stuff that I was doing, but to talk about new stuff. And the truth is that there are a lot of markets where the convexity assumption makes no sense, but the parties want linear prices. So actually, Martin up there is the co-author on one paper that was part of what inspired me to this problem, which was the New South Wales fisheries rights auctions. In New South Wales, due to overfishing, they had cut back the catch that was allowed, and they reduced the number of fish that you were allowed to catch, or the weight of fish you were allowed to catch with any given license. And some of the fishermen needed to go out of business, and others needed to buy more licenses. Well, the ones who were buying more licenses were adding at the margin, and so they were operating on what might be the concave part, possibly, of their value function. But the ones who were selling, they didn't want to. They were already under supply. They either wanted to sell their entire supply of all the licenses they had, or none at all. So we had a serious non-convexity. And in the PNAS paper that Martin has, he talks about the computational methods they use. But we were really interested in the economics of it, which I'll focus on. And in electricity markets, we have these. Everybody knows we have these huge startup costs. That correspond to fixed costs that make that a severely non-convex problem. But in both cases, the parties have the feeling, if I'm selling twice as many fish, or if I'm buying twice as many fish, I should pay twice as much. Linearity to them is a notion of fairness. In fact, it's in the title of Martin's paper, that they want linearity not for the mathematical properties that we as economists often talk about, but because they think of that as a fair way to compensate buying and selling. So, so the new work is called Linear Pricing Mechanisms in Markets with Non-Convexities. And again, it's co-authored with Mitch Watt. And that's what I'll tell you about in my remaining time. So these are quasi-linear models. Everybody has values. the firms who are producing in this model, they're noted by little f, and they have non-decreasing, possibly non-convex cost functions, CF. The consumers have non-decreasing, possibly non-concave value functions. Consumer N has value UN, that's the dollar value of the package that it acquires. There's L commodities, I should say here. And so these are, the domains are the non-negative RL. And I'm going to introduce a new mechanism to you here that you haven't seen before, that we invented recently, that we call our alpha price mechanism. And it has the property that it has linear prices for producers and consumers, but not necessarily the same linear prices for producers as for consumers. It's resource feasible. Now we're going to draw on, some of you may know, I guess you may know in various ways, approximation work. In the general equilibrium theory that deals with non-convexity, there's the Shapley-Folkman-Starr theorem, where they show how you could use linear pricing to get things that are approximately feasible. And for mechanism design, you know, the spirit of mechanism design, we want things that are actually feasible. So our mechanisms are related to some of the ideas from general equilibrium theory, but we have actually feasible allocations. Participation is going to be individually rational. The whole thing will be budget balanced. The computations will be quick, despite the non-convexities. There'll be near truthful reporting in much the same sense as Robert's postal weight, that if the market is reasonably large, you can't gain very much by your best deviation. And we'll have near efficient allocations. We'll get allocations that, again, in a large market, I'll show you the losses on the order of a constant, independent of the market size, from using our mechanism. Then it goes like this. So first of all, an example of the problems that non-convexity causes. This is really a reminder for most of you, because I think this is pretty clear. We have a single firm that can produce individual units, an integer number of units, at a cost of 1 each. Each buyer wants to buy exactly QN units of the good. So the buyer's payoff, if he pays a transfer T, and if he gets less than his desired quantity, gets no value from that, he just pays T. And if he gets at least his desired quantity, he gets QN times VN minus the price he pays. So these are guys who just, all they want is exactly QN units. More they just throw away, less is of no value to them. And in my example, I'll use star to designate the buyers in the efficient allocation when there's some fixed price. And in the first example, there's just 3 buyers who have values of 1.8, 1.6, and 1.2 per unit. And their order sizes are 0.3, 0.8, and 0.1. And now individual rationality, well, for this to be individually rational, the price has to be no more than 1.2. So that means buyer 1, individual rationality alone, it means that buyer 1 would have to be rationed for us to get the efficient allocation. So we have to deal with rationing. And here's another one. If we have a price P that is individually rational for the firm, it has to be greater than or equal to 1. This table, by the way, is the same as the other table, except that the value for buyer 3 has been reduced to 0.8. The efficient allocation gives him a 0.8, gives him his order anyway, even though his value is 0.8 and the cost per unit is 1, because this guy is producing integer quantities. So individual rationality at a fixed price has to fail for somebody. If the price is bigger than 0.8, this allocation, the efficient allocation, won't be individually rational for bidder 3. And otherwise, if the price is less than 0.8, then it's not individually rational for the firm. So those are the problems, the kinds of problems we have to deal with in designing in a non-convex market. So notation, omega is just going to be the allocation, which is x's are the allocations for consumers and y's are the allocations for the firms and the usual L dimensional spaces. Surplus is going to be the total value that the buyers get from the allocation minus the total values that the total cost to the sellers, and the maximum feasible surplus is the maximum over the feasible set of the surplus of the allocation. And we'll have indirect profit functions defined in the usual way. You find the thing that at fixed prices that would maximize the utility of the consumer, or at the output that at fixed prices would maximize the profit of the firm. And here's going to be something that will be more new and more important to us. So Rn is going to be the rationing loss that firm N suffers when the allocation is omega and the price is P. And what's the rationing loss mean? Well, here's the maximum profit he could have gotten. It's pi n of P. And here's the profit he actually gets. At the rationed allocation, he gets un of xn minus p dot xn. So we call this the consumer's rationing loss. And we have a similar rationing loss for the firm, which is the maximum profit it could get minus the profit it gets at the prescribed allocation when the price is specified to be P. And script R, then, is the total rationing loss. So what you're going to need to remember to read the next slide is that script R, which depends on the allocation and some price we specify, is the total rationing losses at that price. S star is the maximum feasible surplus, and S of omega is going to be the surplus you get from the allocation omega. And we're going to try to make this as big as possible, subject to some constraints. So the first result is about the first welfare theorem in quasi-linear economies. And we call it the first welfare bound. So in the first welfare theorem, if omega P is a competitive equilibrium, then omega is an efficient allocation. And for quasi-linear economies, that means that if omega P is a competitive equilibrium, then the value of the allocation is the maximum value. Okay, it's familiar from quasi-linearity. So what we're going to do is we're going to extend the first welfare theorem, reinterpret it as a bound on losses for economies in which we have a price, but there's also some rationing and also some non-market clearing at that price. And we're just going to, extend the first welfare theorem to consider it a bound on the welfare loss, and it looks like this. Now we take any pair, take any allocation omega and any price vector P, any feasible allocation omega and price vector P. And this says that the welfare loss, the difference between the maximum welfare and what you get from omega, well, first of all, it's at least zero. You can't do better than the efficient. But it's bounded above by the sum of two terms. And the first term is the agent's, notice, by the way, there's no P in here. So this is for any prices that you pick that you can use to establish a bound on the welfare loss for any allocation. And what you do is for the price P that we've specified, take a look at what the agent's rationing losses are, how what they get is different from what would maximize their profits or utility, and take a look at the budget deficit. So we have here the total production of the firms. Here's the total production of consumers. We know this is non-negative because the allocation is feasible. So this is, if we don't have market clearing, we'll have some non-negative number here. And we take P dot, or non-negative vector here, we take P dot that vector to get the budget deficit or unallocated production. Now notice, of course, the reason we call this the first welfare bound theorem is that at a competitive equilibrium, there is no rationing, so the rationing losses are zero. And at a competitive equilibrium, there is no non-market clearing. This is zero. And so what we get is that our upper bound is that the welfare loss in that case is zero, right? But this inequality is not limited to market clearing, and it's not limited to what people getting what they demand. It gives you a general statement of what the welfare loss is from some allocation when you assess it using some particular prices. Okay. Okay, and here's the proof. It's not very hard. We'll use star to denote maximizers. Then by definition of the indirect payoff functions, the pi n of p is the maximum profit that n can get. So that's for any allocation you name, that's got to be greater than or equal to un of xn minus p dot xn. Since at prices p, he could have gotten this utility. And since that's true for all xn, you can put in the optimal allocation and get an upper bound on un of xn star. It's at most pi n of p plus p dot xn. And you get a similar inequality for the cost. And you just add them up. And you get that the total, which is the sum of these xn's minus the sum of these costs, is bounded by the total of these indirect profit functions plus p dot xn star minus yf. And feasibility implies that this term, whatever it is non-positive. At the optimal allocation, we might have market clearing or we might not. But in any case, the demand, the supply is at least demand. So this term is non-positive. So we can just drop it and say that S star is at most the sum of the indirect profits. And then we can subtract S omega from it and get this expression. So we've just subtracted S omega. And now we can add and subtract these price terms and regroup. And when we add and subtract these price terms, what we get is by putting in for pi n of p, by adding this term and subtracting that term, we get the rationing losses, and the term that's left over, the p dot yf minus p dot xn is over here. That's the budget deficit, and that's the proof. It's pretty straightforward. It's just substituting in the definitions and as in the fashion that I showed. Okay, so the first idea was this first welfare bound, and now we're going to use that to create a mechanism in the following way. So what we're going to do is we're going to ask, it's a mechanism, we're going to ask the buyers and producers to report their value and cost functions. Then we're going to determine, we're going to actually solve the related convex problem. So we'll determine the concave hull U hat of n and the convex hull C hat of f. And we'll ascribe some demand to the auctioneer. We're going to use this to get feasibility. It's going to turn out that only the auctioneer will be rationed in the mechanism that we run, but the auctioneer will have some demand, and that's how we're going to get feasibility. And our notation is going to be, we used to have S of omega was the total value minus the total costs, but I've got this, yeah, these things aren't popping up in the right order, pardon me. So let me just comment on the whole thing here. What makes S alpha different is that instead of maximizing the total value minus the total cost, we shrink the total value a little bit by multiplying it by 1 minus alpha. And in addition, we put into the objective some value for the auctioneer for what it acquires. And it's going to be a very high up value up to a limit. So it's in this convex problem, it's going to be assigned some of the output. And then we'll find the maximizer omega star of alpha. And since this is a convex problem, we can find supporting prices. And so here's how we'll set the prices then. For the sellers, the price that we get out of here is the price we're going to set for the sellers. And for the buyers, we're going to set the price to be PS over 1 minus alpha. Okay, and we're going to allocate to each agent its most preferred bundle at its prices. So remember, these things don't have to be concave or convex. but buyer N is going to get X hat N that maximizes its value at the buy prices. And seller F is going to sell its quantity that maximizes its utility at the sell prices. And you'll notice that the buy prices are higher than the sell prices because of this 1 minus alpha. Okay. And so how do we do when we set things that way? Well, to get budget balance, we're going to need to set alpha to be, basically, we're going to have some failure of market clearing, and it's going to depend on the size of the non-convexity. This is all Shapley-Folkman star stuff that I'm not going to go over in detail here. But if you take the size of the largest non-convexity, that tells you, how much money you might need to close the gap. So we'll get something that's proportional to the size of the non-convexity. And then we have to collect that from all of the from the agents we have. It's going to be inversely proportional to the number of buyers in the market. And so that's what alpha is going to look like. That's how much we'll have to bump the prices of the buyers. If we use this allocation, what we're going to do is then use this allocation that that I computed on the previous page, and this price for the to do the first welfare bound, we'll use that allocation, and we'll use the seller's prices. And so at the seller's prices, the sellers are selling exactly what they want to sell, so their rationing losses are 0. And if demands are single valued, and this is for you, Shengwu, and all my students out there, by the envelope theorem, right? The rationing losses that are suffered by the buyers are on the order of alpha squared. That is their second order in alpha. And that's for each individual buyer. So if we take the rationing losses for all the buyers, we're going to have to multiply that by n, and we get rationing losses that are on the order of 1 over n. So by the first welfare bound, we conclude that what this mechanism does is the welfare loss is no more than this O1 over n plus basically an O of 1, which is the loss that we get. It's not shown here, but it's essentially the loss that we get from failure of market clearing. There's a fixed sum, up to a fixed quantity that the auctioneer is buying and gets rationed on. And so the welfare loss is.
Paul, can you once again clarify how you ascribe the U hat 0 for the auctioneer?
So the U hat 0 for the auctioneer. So I didn't tell you a lot about that because it's Shapley-Folkman stuff.
Okay.
But we know that that we can put everybody into their feasible production set, except for what we have to do is we have to have a fixed amount that we have to be able to add to put those people into their production sets. Right. And so we have the auctioneer buy that amount.
I see. Okay.
And that depends on the size of the largest non-convexity in the economy. Okay. And we have we give the auctioneer a very high demand for that amount. So we ensure that the auctioneer is buying enough. And then no matter what allocation we make to the others, which might be infeasible by itself, we can ration the auctioneer and take some of the stuff that would have been given to the auctioneer so that everybody's production is feasible.
Okay, thanks.
So that's the gist of it. And then what are the properties we get from this mechanism as a result? First of all, it's resource feasible. So we've constructed it so that the only person that's rationed is the auctioneer, and he's left with some non-negative amount, which is leading to this inefficiency from non-market clearing. It's individually rational. Remember that when we did the optimization, well, it's individually rational because everybody is buying their most preferred quantity at some prices. And if they don't like it, they can buy 0. The maximum welfare loss from overproduction is a constant. It's on the order of the size of the largest non-convexity in the economy. The budget balance, well, basically if we can pick alpha, we pick alpha just big enough to balance the budget, it's going to be on the order of 1 over n. It's going to be more precisely on the order of d over the size of the market, which depends on how many buyers and how many sellers there are. If the maximum values are unique, then the welfare loss from rationing is on the order of 1 over n. I've already showed you that. It's going to be near truthful for large markets. Now, this is an interesting thing that, remember, as we learned from Robertson Postlewaite and subsequent work that others have done, in a large market, if a buyer can't have very much effect on the price, then he can't gain very much by misreporting. And here, each guy is buying his most preferred, is being assigned his most preferred bundle at the price and can't have very much effect on the price. So it's very much the same argument that Roberts Postlewaite used to show that neither the buyers nor the sellers in this case can gain much by misreporting. Now that's a little bit subtle in this context because other rationing mechanisms, this is something we struggled with. In other rationing mechanisms, if you misreport, you might both affect the price, maybe only a little bit, but you might also affect how much you're rationed. And so we have to ration in a way that ensures that people don't have an incentive to misreport in order to control the rationing. And this two-price mechanism accomplishes that because people are getting their most preferred. Essentially, the buyers are being rationed by having a price set that's a little higher than the seller's price, and that's what's doing the rationing, and they can't have much effect on that price. That's giving us our incentives. And you know, the convergence can be faster. We can, if we have a if we don't have non-convexities on both the buyers and sellers side, if we have non-convexities in production but not consumption, then we can do things like we can use a single price and introduce some rationing on the buyers, and it turns out we can get faster convergence for those models. But it's a little different mechanism, so I'm going to pass that over here. Well, goodness, I got through that faster than I expected. So I think I have about 5 minutes to spare, roughly, and maybe I'll just say that, you know, again. Mitch Watt's there somewhere at the conference. Hi, Mitch. First time that we have presented this, and it just that using prices in non-convex markets appears to be something people want to do. We've been unable to say much in the past about linear prices, and we think that being able basically to explain what the welfare loss is for many linear prices with rationing and non-market clearing gives us a suitable extension of the first welfare theorem that we can use to analyze markets that are close enough to convex that we can keep these numbers small. And I guess that's it. I'll stop there.
Well, wonderful. Thank you, Paul. You know, past, present, and future all in an afternoon lecture. So that's amazing. This was wonderfully interesting. I think we indeed have a few minutes. So if either from the panelists or from the attendees, you have any questions, then feel free to raise them. But we can also, of course, wait until a little later for the reception. But given that we have a bit time.
I have a very naive question regarding the first part on your spectrum auction, Paul.
Yes.
The multiple round auction looks just theoretically very complicated with huge number of possible equilibria, Nash equilibria, because people can condition delicately on past behavior. So I just wonder how you think about it. that those equilibria don't arise in practice, or what?
No, there aren't a lot of equal. So the analysis the theoretical analysis that we did, okay, so every theoretical analysis involves some steps from some abstraction from reality. And I want to go circle back to that because it might be that's what you have in mind. But the theoretical analysis we did was about stations that, companies that owned a single station. And it turns out not only do they have a dominant strategy, they have an obviously dominant strategy. That is, if you have a station and it's worth $25 million to you, and it's a clock auction and my opening offer to you is 100 million, and your choice is to say yes or no. And if you say yes, you keep your station and that's fine. If you say no, you keep your station and we'll find you a place to broadcast on the air. But if you say yes, we might buy your station for 100 million. And if we don't, we'll give you another choice. So it's obvious that no matter what everybody else does, and no matter how I'm doing this computation, you can't do better than to say yes. Okay. And now in the actual auction, we had some. And the reason we did the analysis that way, by the way, is when we began this talk to the FCC, they told us, somewhat misleadingly, they were talking about full power stations. They said there's only a few markets in which people are allowed to own or have succeeded in owning more than one broadcast station. Turns out that wasn't true about low power stations. It was only true about full power stations. So that left a hole in our design that some hedge funds managed to exploit, where they were able to, especially in Pittsburgh, acquire a large number of low power stations, which we also had to buy. But we had imagined that that most of those who were selling were the small family-owned stations in individual areas, which would have one station for sale. We wanted to make bidding easy for them, and we wanted to have a mechanism that worked well when most stations were like that. We ended up in a setting that was a little bit different than we anticipated. But anyway, that was what the theory was about.
Okay.
Wonderful. Sergio had raised his hand politely.
Yeah. Paul, nice to see you, Paul.
Nice to see you too.
So I had a question about the latest paper, the alpha paper, the alpha equilibrium. Now, it's a nice trick having this uniform alpha on one side. Is there any theoretical reason, besides simplicity, of course, because it seems to me that, of course, with non-uniform alpha, you can probably improve on your measures. So the question is, how much, or is this, I mean, do you know anything about non-uniform alpha in short?
Not yet, we don't. I agree with you that we have played with the possibility of doing other things where we have the key. Well, one of the key insights is that we need different prices for buyers and sellers. If we're going to have non-market clearing, and if then and you had the same prices for buyers and sellers, you'd have a budget deficit, just by definition. So we need different prices. And this really simple way of introducing different prices has a loss that is second order, right? It's which seemed like a pretty good place to start. We might be able to do still better, although I think we're more interested in the case right now. What Mitch and I are more interested in is looking at the case where the non-convexities are just on one side, let's say production, and we want to see whether we can avoid the non-market clearing loss. The O1 loss, the big loss, is from non-market clearing. It's because the auctioneer has to buy some stuff, which means throwing away some goods. And if we have if we don't have any non-convexities on the buy side, we should be able to eliminate that loss and just have the rationing loss. And so our big effort really is to eliminate the fixed loss and have the total loss be on the order of 1/n. And then, relative to the market size, it's then on the order of 1/n squared, and that's a really good result. So, so we're going that way first, but we're aware that determining those.
Of course, the uniformity could be on other parameters, like relative rationing or other things like that. So you could still have only one parameter that you play with, but you could plug it in different places.
Yeah.
The question is, then to select which one is really the one that works best, right?
Yeah.
But it's a good start.
Thank you.